Okay, so I want to do another Stokes theorem question. Everything above the red line, um, all of this stuff, I guess, this is all from the previous problem. So I want to do problem number 2. Okay, so the last time in problem number 13, how did we use Stokes theorem? Well, we were given a line integral over a closed curve, and we converted it to a surface integral. Okay, now we're starting with a surface integral. Um, I'm going to kind of go through 2 steps, but once you see the idea, you can just collapse this into 1 step. Okay, so S is the top and 4 sides of the cube with these vertices, minus 1, 1, 1, 1, minus 1. So all the different combinations, eight different vertices. And it says top and 4 sides, but not the bottom. Okay, we want to compute the surface integral of the curl of F over this surface. Okay, so now at first, we're going to go the opposite direction in Stokes' theorem, or the opposite direction from what we did in problem 13. This is what we're given. We're going to use it. We're going to use Stokes' theorem to compute this line integral. Okay, but actually, we're going to change it. That's not going to be the ending. This is like the intermediate step. So the boundary of this region, the boundary of this surface, is going to be in the z is equal to minus 1 plane. And this is at 1, this is at 1, this is at minus 1, this is at minus 1. Let me use a different color. Okay. So this should be a square, looks like a rectangle, so whatever. Okay, now all surfaces have outward orientation, so that means that this boundary, and I'll let you think about why, should have counterclockwise orientation. Okay, so Stokes' theorem says that the surface integral of the curl of f is equal to the line integral of just f. Okay, so if we call this curve C, then what we know is the surface integral of the curl of f, this is by Stokes' theorem, this is equal to the line integral over this curve f dotted with dr. Okay, so now this is the thing that we want to compute. Okay, conceptually now this is the thing that we want to compute. We forget about that we even had this surface integral that we were computing to begin with. So now let's just imagine that this is the problem that you're given. Forget about anything else from the rest of the problem. Let's imagine that this is the problem that you're given, and someone said, "Hey, can you compute the line integral of this vector field over this closed curve?" Well, if that problem came along to you, you would say, "Hey, I can use Stokes' theorem to write this as a surface integral." But what is the surface you're going to pick? It's not going to be this original surface that we're given. It's going to be, let me try to fill it in. It's just going to be this square right here, right? That's the surface integral that you're going to compute this as. Okay, so this is equal, so I'm going to call this surface S2, since I'm already using S. This is surface integral over S2 of the curl of F. Okay, and so how is this computed? Well, this is just the surface integral over S2, the curl of F dotted with the normal vector ds. Okay. So now we're going to compute it this way. So now we're going to fill in each one of these pieces. So this is going to be, we'll see. So the curl of f, so this is f, so the curl of f, I'll let you guys compute this on your own, but it is x squared z minus 2x y z minus xy y minus xz. That's the curl of f. Okay, now the normal vector, let's think about what the normal vector is. So the surface that we're integrating over is this square right here. That's the surface. And because the boundary curve has counterclockwise orientation, it means that this surface has upward orientation. So this is taking place in the z equals -1 plane. So this is the x-axis, and this is like the y-axis. Okay, so the upward pointing normal vector is just 0, 0, 1. So the normal vector is 0, 0, 1. So what this tells us is that the curl of f dotted within is just equal to, didn't mean to put the bracket there. Let me just get rid of this. This is equal to y minus xz. Okay, so now there's an important observation that we're going to use here. Whenever we are computing the surface integral and the surface is in a z equals constant plane, this is just like, sorry, this is just like computing. This is essentially just like computing a normal double integral. Okay? So what do I mean by that? Well, the parameter domain is just going to be x goes from -1 to 1, and y goes from -1 to 1. So x is going to go from -1 to 1. Y is going to go from -1 to 1. Now the gradient, the curl of f dotted within, what is that? Well, notice that this is taking place in the plane z is equal to -1. So if z is equal to -1, this means the curl of f dotted within is equal to y minus x times -1. So this is equal to y plus x. Okay, now here's what I mean when I say that we compute it just like it's an ordinary double integral. When the region, so once again, when we're doing the surface integral of a surface that lies in a plane like this, z is equal to some constant, like z is equal to 0 or z equals 1, or in this case, z is equal to -1, the ds is just dx dy or dy dx, whichever order you're doing this in, or ds dt, whatever the variable names are. Does that make sense to you? I hope it does. If it doesn't, just think about it, or just trust me, but hopefully think about what's going on here. Whenever the region is in a plane, a z equals constant plane, uh, this surface integral is just like a normal double integral, where you just look at what the region is here. Y goes from -1 to 1, x goes from -1 to 1. Okay. And then if you do this integral, you get that this is equal to 0. Okay, so the point of this problem is the following observation. If two surfaces have the same boundary curve, then the integral of the curl field on one surface is equal to the integral of the curl field on the other surface. So let me say this one more time. If two surfaces have the same boundary, the surface integral of the curl field on one surface or over one surface is equal to the surface integral of the curl field over the other surface. Okay, now this only works if you are doing the integral of a curl field. In other words, the curl of some other vector field, and it only works if the two surfaces have the same boundary. And you also have to make sure that you get the orientation right. So for example, if we think about this square as being part of this cube here, then the boundary or the orientation would be downward pointing. The normal vector would be 0, 0, -1. But we're not thinking of it that way. We're thinking of it as its own surface whose orientation is given by the counterclockwise orientation of the boundary, which is the upward orientation. So think through some of that, but this is a very good way to know how to compute surface integrals of curl fields.